Good afternoon, ladies and gentlemen, and welcome to the SAIEE Gauteng Centre webinar on debunking nuclear myths. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel, and by default, it is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with each other. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel. You will see the QR code appears on your screen. You can scan that and register. It is free of charge. And the recording of this webinar will be placed under the Central Gauteng Centre playlist. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to our host for tonight. It's Mr. Tsoledi Moloi, who is a Technology, Knowledge and Leadership Chair in the Central Gauteng Centre, and he is an Instruments and Control Systems Technician at Ardagh Glass Packaging Africa Wadeville Factory. He specializes in maintaining and developing new control system strategies that focus on forming quality glass packaging containers. Tsoledi graduated from the University of Johannesburg with a Bachelor of Engineering Technology in Electrical Engineering and is an enthusiast for process automation and control, mainly industrial process automation. Having joined the SAIEE Central Gauteng Centre has exposed Tsoledi to diverse engineering aspects. Over to you, Tsoledi.
Good day to the viewers and everyone. I would like to welcome you to our webinar today, Debunking Nuclear Myths. Today, we are very fortunate to be hosting Professor David Nichols. He will be doing his presentation regarding the topic at hand today. So, ladies and gentlemen, this is Dr. David Nichols. Mr. David Nichols has extensive experience in the nuclear and energy sectors, beginning as a nuclear engineering officer in the Royal Navy in the 1970s. He joined ESCOM in 1984, advancing through its nuclear engineering department and serving as technical support manager at Quebec in the early 1990s. He led the Pebble Bed modular reactor project from 1996 to 2004 and became the technical leader of ESCOM's new nuclear build program in 2007. He was appointed General Manager of Nuclear Engineering in 2010 and Chief Nuclear Officer in 2016. In January 2020, he became Chairperson of the South African Nuclear Energy Corporation. Nichols is a registered professional and chartered engineer with a BSc Hons in Mechanical Engineering and a postgraduate diploma in Nuclear Engineering. Well, ladies and gentlemen, this is going to be our presenter for the topic today. And before we begin, please make your way towards the handouts menu and make sure that you get our What Now magazine February edition. And also feel free to download the presentation that will be done by Mr. Nichols today. And in that order, welcome, Professor David.
Hi guys, can you see the screen?
Yes, perfectly.
Okay, fine, right. I've asked to dispel nuclear myths in 45 minutes, which is a bit of a challenge. So I have put the presentation in the document section. Please understand, people, that I'm going to go through this quite quickly because there's an awful lot to do. Let's start with what I saw as the nuclear myths, and I'm going to go through each one in turn and try and show some facts that may explain why they aren't necessarily true. So the first one I always quote is nuclear is too expensive. The second one, which goes with the first one, is that nuclear can't be funded. The third one is that nuclear power stations cannot load follow, that they're only base load machines and they make power and nothing else. The next one is takes far too long to build them. And then just for good luck, nuclear is unsafe. It won't help climate change, and there is no solution for nuclear waste. I think I've covered the majority, and I'm sure there's some more myths, and I'll happily analyze in question and answer. Let's start off with nuclear is too expensive. And all my presentations made of slides largely of information I'm quoting. So this is an interesting analysis. This was done for the Financial Times in UK in 2019, still valid today. And it quotes the cost of nuclear plants. And they did analysis of nuclear plants. There were 34 actually delivered nuclear projects around the world. And they came to the conclusion that a first of a class nuclear plant in the USA or Europe can cost $9,000 to $12,000. I'd argue that's even low by some of the problems they've got in the first world now. But in reality, only 15% of nuclear plants cost more than $5,500 a kilowatt. 45% were between $5,500 and $3,500, and 40% are below $3,500 a kilowatt. I'll explain these numbers a bit later as I go on. I'm going to be quite quick in this presentation. This is an interesting graph to explain why nuclear power can be misquoted. This is US data, in fact, from Westinghouse presentation in 2003, but it's valid. The capital cost of existing US nuclear plants in the year they were commissioned and what their costs are. And the nice thing about the US is they keep lots of good records. So here we have a situation where you can see the 100 and something nuclear reactors the US has built, starting in the mid-60s, going through to the mid-80s when the previous building boom stopped. What's interesting is that these are the same regulator, in other words, the US NRC, the same technology, in other words, they're all water-cooled reactors, and the same industry, the same players are in go. But what you can see is the ratio between the most cost-effective one delivered and the most expensive one is 5 to 1. And that tells you that project management is the key issue in building nuclear plants. So I will say, absolutely, nuclear plants, if you don't know how to do it, can become horribly expensive horribly quickly. And experience and any nuclear project has to be based upon a team that knows what they're doing. If we look at a more recent example, for those who don't know it, United Arab Emirates ordered 4 reactors. And I'm sorry, this slide is in Norwegian. I apologize for the language, but I'm not Norwegian. But it's pretty obvious what it says. What this is that they built 4 reactors in Braqa, which is in the UAE, on a turnkey contract. And this is analysis of the cost of building them. And what's interesting is these are the OPR one, that's 1,000 megawatt machines, and that's the cost for Korean reactors, Shinkobi 1, 2, 3, and 4. Then they built what's called the APR 1400 megawatt reactors, and that Shinhal 1 and Shinhal 2 are actually built in Korea, where they've got the background and the industry. But what's interesting is the ones built in the UAE, the export machines, the first one cost the best part of $6,000 a kilowatt. The second one fell to about 5,000, and the fourth one of the series was down to being very close to the price in Korea. So the first answer on nuclear costs is you've got to look at nuclear costs and saying, are you building a first of a class? Bring in a good vendor. This is the other thing about nuclear is the cost of capital. This graph is just you can see the graph. Each line here represents a given capital cost for a nuclear plant. The top one being $6,000 a kilowatt, which is the kind of price that you may end up paying if you're buying a first of a class machine, and the last machine and the lowest price is $2,500 a kilowatt, which is the kind of price they're currently looking at in domestic machines in South Korea, Russia, China. What's interesting is that you change discount rate you assume for the project. If you look at the $6,000 a kilowatt, that's $2.20 a kilowatt hour at 10%. But 10% real discount rate is pretty exciting to an investor. But if you go down to 2% discount rate, which is the actual cost of capital in the real world, you're down to almost, say, $750, $800 80 cents a unit. So it's more important to discuss how you finance a nuclear plant rather than actually what the capital cost is in some ways. And certainly studies like the South African IRP, which assumes 8% cost of capital, bear little relationship actually to the real cost of capital, I'll show in a second, which is down in this region down here, 3%. Moving on, just in case you think nuclear is expensive, I happen to get this graph from the US Energy Information Agency, 2023, and it plots countries in the world with the cost of power in US cents per kilowatt hour versus dollars per hour versus the percentage of the supply that's in wind or solar. And there's two things that are interesting. The one just interesting, clearly there's a nice relationship here, which says the more renewables you have, the more expensive your power is. But also, these countries I picked up here, Turkey, China, India, South Korea, UAE, and Russia are all building nuclear plants at the moment. So, and Saudi Arabia's got a tender document out. So it's interesting. Maybe nuclear isn't so expensive. Just of interest also in terms of cash flow, someone will tell me that natural gas is clearly a cheaper solution. If you look at actual funding costs, and this is based on a 4% real interest rate, which is actually quite high, and you compare a nuclear plant funded by export credit agency finance with a nuclear plant, given reasonable numbers, I put $5,000 a kilowatt. You can look at the numbers at the bottom when you think. What's interesting is that for the first 18 years, while you're paying the debt off, the actual cash flow for the nuclear and for the natural gas is almost the same. The amount of foreign exchange of the dotted line, so you can see the foreign exchange for the nuclear plant is less than the natural gas plant, because the natural gas plant is importing LNG, and then at 18 years it falls apart nicely, which explains why Coburg is now sitting as a really cost-effective plant for the South African grid. So that's the first one. I've just gone through very quickly, and I can come back in questions. But you clearly can't get the money. Well, maybe you can. The Egyptians are building 4 nuclear units, 1,200 megawatts each. That's what 4,800 megawatts the block. They're also including in that a full desalination plant to provide desalinated water, the capacity of which is probably about twice what we use in the Western Cape. What's interesting is that the Russians have loaned them $25 billion to do this, and they are quoting an interest rate of 3% annually. Now, this is nominal interest rate in dollars. US inflation is about 2% over the last 10 years, if you ignore the recent crisis, which means that the actual value that the Egyptians are paying is 1% real. And of interest, Standard & Poor's rates Egypt as worse than us in terms of credit rating. So that's straightforward. What's interesting is you only start repaying this debt when the plant starts up. In other words, you can see that the loan will be used by the Egyptian side 13 years between 2016 and 2028 as they construct the plant, and they'll start repaying it only in 2028 over 22 years. Quite interesting little discussion. This, by the way, is a statement. I use this as an example because it's a statement actually issued as a press statement by the Egyptian government, not some vague understanding. So yes, you can raise money, and in fact, every single nuclear export plant in the world is funded this way, with the exception, oddly enough, of the UAE job because they paid cash because they're an oil country in the Middle East. So if you think we can't get those rates, this happens to be at the same time period in March 2020. Annual forecast, Eskom gets export credit facilities for other things. These aren't for nuclear. What is interesting is to look at the interest rates that we actually incurred in Eskom for volumes of money. And what you can see is interest rates that are down 1.5%, 2%. The 9% is for somebody that they got South African Rand loan, but that again, if you think of 6% inflation, is 3% real. So you can see that export credit agency finance is available for all nuclear plants. Historically, Coburg was built with it, and it actually is very competitive, to put it mildly. Okay, but we've covered that one, and everyone's telling me that's no good. We can't load follow. We're base load machines. Yeah. Nuclear plants are normally run at full power as base load because they have the lowest marginal cost of running. And this again is extract from SAIEE annual reports of 2024. And this is the primary energy cost of the plants. In other words, the extra money that Eskom pays to run that plant for an extra megawatt hour, if that makes sense. So it isn't the overall cost. So what you can see, this is the cost that Eskom would avoid if it did not run a plant. So you can see that essentially coal is about 50 cents, 55 cents a unit is the cost of the coal. That's what you don't use it about. Nuclear is about R1.10 the unit. Sorry, 0.1, 10 cents. So I get it right a second. OCT is about 6.5, 7 random. IPPs, that's the renewables, are about R2.30, R2.60. IPPs, very similar to OCT, they're playing natural gas thing. Renewable IPPs, again here, and the last one is, at the bottom is Korobasa being imported. What is clearly the case if you're looking at these numbers in national control, you always leave nuclear running as long as you can. It's the last thing you unload because you will save least by not running it. Your fixed costs are fixed costs. Of interest, the overall cost of running Coburg at the moment, when I was there as CNO, was running at about 40 cents a unit. So the operating cost of Coburg, about 30 cents a unit, was the fixed cost of having the plant, manning it, maintaining it, and everything else, and about 10 cents was the cost of actually buying the fuel. So that's why they don't want. This actually is a graph of the, which I found is pretty standard, of actually how much can you technically change load in large machines. Nuclear can classically do, and it's a standard feature of all large modern PWRs, is 5% per minute ramp rate, down to about 50% power. Normally, you can in fact go lower than that. So that's the nuclear. What a nuclear plant could do in terms of changing load. A coal station has about 3% per minute. That's that. In other words, all Eskom's coal stations can theoretically change load slower than Coburg can. And of interest, at the bottom end of the range on an Eskom coal station, you have a limit. You have to put oil in the boiler to keep the boiler up. Coburg, in theory, can go down to about 20% power, but we wouldn't do that. And then gas turbines are equally not exactly maneuverable. So here's an interesting question: that nuclear can change load faster than a combined cycle gas turbine or a coal station. And you may ask, well, why is this? And the answer is submarines. This is a bit of history for you. That's a Swifter class submarine. I used to serve on one of those, hence you saw my input. I was ex-British Navy. And you may guess that nuclear submarines are designed to change load as fast as dramatically. In fact, we could change load at amazing rates, sort of 50% a minute. And that's the basic technology we're now looking at. So therefore, the idea that you can't make PWR technology, which is classical, load follow is not reasonable. You just don't want to because it's too expensive. But is there any proof that you actually can run a nuclear plant in load following mode safely nowadays? Well, I got this graph on Golftech 2. Now, Golftech 2 is a nuclear power plant in France. It's a 1,300 megawatt unit, and this is its figures for June 2013. Now, the French, because they have an all-nuclear fleet, along with hydro, which is run-of-river hydro, in other words, they don't actually, they always run, the nuclear has to load follow. And so some of their stations are committed to load following, and that is a load following graph of Golftech over a month. They shut down for 2 weekends. They went to low load of the 2 weekends. You can see it's below 50% power, that I commented earlier. And you can see day and night. At night, they ramp it down, day they ramp it up, and during the day, load follows. So concept that nuclear plants can't load follow, no, we just don't want to because it's more cost effective. If you had to, you can. It's not an issue. Okay. The next one, and I'm going through reasonably quickly to give time for comments, is but they take far too long to build the nuclear power station. There's no point going there. It takes decades. And so again, a bit of world experience for you. This is France, real experience. The French decided in 1973, at the point of the oil crisis, to go nuclear in a big way. And this is the graph of their actual production of power from World Bank, which shows you between 79 to 88, they went from 55% fossil fuels to 9.5% fossil fuels, which sort of indicates they can change power quite quickly. They can change. So this is the result of a build program in a country that wasn't previously building many nuclear plants. They brought the first plant on, the first water-cooled reactor on in 73, and that's the result they achieved. So that's quite fast. This is a bit of a complicated graph, and I'm explain. This is an analysis of the BP Statistical World Review, about 2020, but it doesn't matter, of what was the deployment on a per capita basis of megawatt hours by different technologies in different countries. So the best ever was Norway at the bottom, hydro, and they had 0.8 megawatt hour per capita and annual average yearly from 1989 by building hydro dams. The next is Sweden's nuclear program, 76 to 86. The next is France's nuclear program. The next is Finland's nuclear program. The next is Canadian hydro, Belgium nuclear, all the way up, and then you start getting into the wind ones. The Sweden wind is what, 0.2. So essentially on actual world data, if we seriously want to move this country to a low carbon environment, it is pretty much that nuclear is historically the fastest way, unless we can build a large dam. And I will comment to you, I would love to move the Grand Inga Dam from the Congo to the Free State. I'm not sure we can do that. So if you can't do that, the quickest way of getting power transfer to low carbon is to actually go with nuclear. This of interest is just the construction dates of the Chinese nuclear plants, and each black dot is a Chinese nuclear plant. The funny colored dots of interest, those dots up there, you can see those dots up there, that actually is the construction of the AP1000 and EPR. That's French and American reactors built in China. And as you can see, they had problems because the French and the Americans had not finished the design before they started building. The other funny one up here, that's right up here, is in fact the high temperature gas core reactor, which is a PPMR type reactor, and it took a long time because it really is an absolute first of a class reactor in the world. But the main dots are the main light water reactors, Coburg type reactors. These two here, and that are actually in Pakistan. They're export machines, and these machines are other Pakistani reactors. So what you can see is we're coming out at a figure, probably a good trend line would tell us at about 5 years from pouring concrete to making power. This is the average over the years. What's interesting is the average construction time peaked in the 1980s, largely driven by US reactors that hit all kinds of regulatory things. But in general, 5 years or so seems a reasonable number for building. So that's, and that again, the 5 years is for when you start pouring concrete. Clearly there was work before that in terms of getting ready for it. But clearly we all know that nuclear is unsafe. We've been told that enough times by everybody. So I will try and just do that one quickly. This is the mortality rate. This is, I think, about a late 90s document. It's still valid. And that's from the World Health Organization and other people. Your average coal station in the world kills about 161 people per 10 to the 9 kilowatt hours. China's pretty bad. America's better. Oil is 36. Natural gas is 4. Biomass, which is really is 24. Solar rooftop is 0.44, which is higher than wind. And the reason it's high, by the way, is simply because somebody worked out that rooftop solar requires guys to be on roofs to install it, and someone did the analysis of exactly how many guys fall off the roofs in the States and kill themselves every year, and they put that back into how many hours people spend on the solar rooftop and work the death toll. And you can see nuclear is down at 0.04. I'll give you a different one a bit later on. What's interesting is that includes Chernobyl and Fukushima in that death toll. We've been running nuclear plants for about 70 years now, so it's not like it's going to hit us sometime soon. Safety-wise, this is just of interest for Coburg specifically. The NR has a limit, which is quite a tight limit, which says that the average person who lives on the site boundary, this is not the person in Cape Town, this person living on Coburg site boundary, has about a 1 in 200,000 year chance of actually dying because of Kuberg's accident. The actual Kuberg data, which is from the analysis NNR accepts, put us about 1 every 100 million years. And I'll just put a comment to you, that actually is comparable to a meteorite wiping out Earth, as in end of all life on Earth. So I think we're not too badly off. And lastly, there's a graph before I move on to the next thing. This is the loss of life due to nuclear power versus in terms of life expectancy going down in years versus fossil fuels. Yeah, you can see that there's a very small impact in Chernobyl. They reckon less than 1 year for the small area around Chernobyl, less than 0.1 year. That's 1 month for the area immediately around Fukushima. I don't debate that. This is China's industrial zone, India's industrial zone, and the rest of the world. Looks like there is no comparison. If you want to be healthy, live near an ex-nuclear station. I think we can see that from living in Cape Town versus living on the Highveld. Next claim made is that nuclear will not help climate change, because clearly nuclear is a climate change problem. Well, this is the UN Economic Commission for Europe. They analysed life cycle greenhouse gas emissions across all technologies, and shock. The nuclear is averaging 5.1, which is the lowest of any technology. Lower than renewables, lower than PV, lower than CSP, clearly way lower than coal. So if you want to get rid of climate change, you go nuclear, and it's better even than hydro, which has some issues in terms of methane. Just if you look at how well countries have done when they tried to go climate green, this is an interesting chart. I'll explain it to you. This basically is the European Union from 2020 to 2021. The numbers haven't changed. And what each dot is, each color is a different country. Each dot is for an hour, 1 hour period, in terms of how many megawatt hours was made in that hour and what was the CO2 emission in that hour. And what you can see, this big one here is Germany. Does get quite good occasionally, but normally it's up here. Here is Poland, because that's very much like ourselves. That's burning coal almost exclusively. Italy, Spain, UK, combination of all three things: bit of hydro, bit of wind, bit of solar, bit of nuclear. This is France, which you can see is looking pretty good. There is Sweden and Norway, which are, in the case of are massively hydro and nuclear. That's what the Swedes have got, is nuclear and hydro, and Norway is pure hydro. And then you've got Belgium but so what you can see is the country that tried to do it, this solution, which is the German solution, doesn't actually work. This solution, which is the French solution, maybe it does. And then lastly, just in this section, is that there were there were 7 big grids that have actually decarbonized, and they've all done it with nuclear and hydro. There is no decarbonized system in the world running on renewables. Nice idea, we may get there eventually, but certainly there's no history to support it. Okay, and the last thing, not quite last thing, almost, we all know that there is no solution for nuclear waste. We've been told that 1,000 times. Well, let's look at nuclear waste a second. This is the South African disposal site at Valputs for all the waste from Kuberg and Pelindaba for what's called low-level waste. And this basically is the waste that is clothing and contaminated items, but very limited. The activity has a half-life of maximum of about 30 years, strontium and cobalt. And so in about 300 years, this will decay away completely to the background. That's low-level waste. You've got intermediate-level waste. The difference is this is process waste from the nuclear plant. And these concrete drums, we mix the waste with concrete. And so in the middle of that concrete drum, there is a slug of concrete mixed with nuclear waste. And again, same sort of half-life, slightly more activity, otherwise than that. But the real problem is clearly the spent fuel, which everyone knows we haven't got a solution for. Well, maybe we have. This is the spent fuel pools at Kuberg or somewhere. Fuel comes out of Kuberg, is put in the spent fuel pools. We then, and we're doing it at Kuberg now, we then take the fuel, put the fuel out of the racks and put it in dry storage casks. And there's a little lady standing next to a dry storage cask. The cask weighs about 130 tons, contains normally about 24, 28 fuel assemblies, and you stack them here, the interim store at some US plant, just stacked them in the same at Coburg now, and they can stay there comfortably with almost no cost involvement for the present analysis showing well over 100 years. What you do with it then? Well, you then dig a hole in the ground and you bury it underground, about 500 meters underground. That is well established. Why haven't we done it? Because it's expensive and there's no need to do it. But this is the project in the world to do that. The most advanced one is Posiva in Finland, and they are literally commissioning it as we speak. They are starting to finally dispose of nuclear waste there. These are other countries, France, Russia, Sweden, and so on, which are going forward in the same way. There is no problem we know how to do it. It is funded. ESCOM has put money aside for it, or has put a provision aside for it. So as Nexa, there is no problem in disposing of spent fuel. The other questions often raised is, but what about decommissioning? And decommissioning costs we can quote forever. I just pulled the NRC out because they've done more of it. The NRC has quoted that in their 2022 document that there are many factors that affect reactor decommissioning costs. Generally, costs range from $300 to $400 million. Sounds like a lot of money. Given the replacement cost of 1,000 megawatt nuclear reactors in the order of $5 billion, this is less than 10% of the construction cost, because the US reactors are about 1,000 megawatts. For the sake of economic evaluation, I think 15% will be used. This is the way it's done in Coburg, and it's generally in line with the percentage used in the Coburg decommissioning provision, and it's used in the OECD NEA reports. I won't go into the details of that. So what does 15% add to the cost of the reactor? Well, I mentioned discount rates earlier, and this is just if I put money aside in an investment fund at the beginning of life of 60 years to decommission the plant at the end of life. Clearly, if I get a net discount rate of 0, I need 15% of the capital cost. But if you start talking about, let's say, 3%, 4% discount rate, which is very conservative, it's a 2% impact on the capex of the plant. What is true is that virtually all the nuclear reactors on Earth currently operate and put decommissioning funds away as they operate. Coburg does that as a provision in the ESCOM books. In the ESCOM books, you'll find it. And what's really interesting in the Coburg books, just like Heartedly, is that Coburg's now had life extension, so its decommissioning provision assumed decommissioning this year. So if we're now decommissioning in 20 years' time, that then means they can claim some money back from that decommissioning fund because it's only got only be used in 20 years' time. And just in case you think this has never been done and no one's ever decommissioned a plant, this is the USA, and the black dots are nuclear reactors that have been decommissioned and released for general use. So this isn't decommissioning in progress. These black ones have actually been decommissioned. I apologize for my dogs in the background. The blue ones are currently decommissioning, and the reddy orange ones have actually are what's called safe store. In other words, somebody has said, we will not decommission it now, we will put it in a safe condition and leave it. And of course, the longer you leave it, the more it decays away, the cheaper decommissioning becomes. So what's the conclusion? And I've been going quite quickly because I want to give time for questions. And the conclusion is this: what is the safest and cleanest source of energy? And this is again from different studies. The references are below it, but it's a well-known graph. What it says is that if you want something which has got low greenhouse gas emissions, you end up with, nuclear is 3 tons for every gigawatt hour versus 4 tons for wind and 5 tons for solar. If you want one that's safest, you end up with nuclear is slightly more dangerous than wind and solar, but they're all pretty much a non-starter. So there is no serious argument in the studies. But then, of course, you get to what is, I would argue, the problem we face as an industry is this: are we looking for an efficient solution or a politically correct one? And I quote from EarthLife, in fact. EarthLife says, the nuclear energy campaign stands in opposition to the procurement and development of new nuclear power The construction of a new nuclear plant would mean fewer renewable technologies to be deployed, as well as their delay. The intended outcome of this campaign is to increase the share of renewables in South Africa's energy mix. I find that funny. It isn't to make it the cheapest, or to make it the least emissions, or to make it the safest. It's to make explicitly to say we support renewables. We don't support low carbon. We just support renewables. And then you've got statements. And this one was done by the Earthlife's Africa's program officer, who said nuclear energy is not the answer to climate change. It is completely carbon intensive. I think we can mention that earlier. So with that, I am come to the end of my presentation. I rushed through it quite quickly. I hope that made some sense. And I will wait for any questions that you may have.
Thank you, David.
I'm waiting for, okay, yeah.
Sorry. Soledi, you with us?
Yes, I'm still here.
Okay, we have
a question.
Yeah. So Mr. John Wilson is asking, how much was South Africa quoted when they went to RFI recently for NPPs?
The RFI came with a range of costs. The lowest cost, I believe, was about $3,000 a kilowatt. And that was, I think, but essentially, the estimated costs that came back from the RFI were in line with the expectation of between, let's say, $4,500 to $5,500 a kilowatt. The nice thing about nuclear plant is that you end up with a turnkey project. You end up with export credit energy financing, as I mentioned, and a turnkey project, so you end up with a fixed price on the plant. The risk is taken by the vendor, rather than Medupi, where Eskom glued everything together and took all the overruns. But no, it was in line with the expectation for the bidders who are, I would say, serious constructors of nuclear plant. And that, by the way, is the Russians, the Chinese, and the Koreans. They're the guys who are doing it right at the moment. You're looking at between $4,500 and $5,500 a kilowatt.
Another question here from
Looking at
from Offended Noah. Well,
yeah,
they're asking the South African PBMR was promising with its Brayton cycle. Why is there no appetite to tackle the Brayton cycle PBMR challenge again?
Oh, that's the answer to that question is that we had the PBMR going and it was closed down for reasons that are in themselves a webinar, its own thing. All the current pebble bed projects, including the Chinese one that's physically running and is commercial today, because the Chinese have built one with the steam cycle, run on the steam cycle. And they do that because they think it's a less challenging technical approach. I'm not sure I agree with that. Clearly, I ran the PBMR project. I believe that the logical way of doing high temperature gas cooled reactors is a direct cycle machine. But the reason that no one's doing it is that everyone's being very conservative. The biggest problem in the nuclear industry is that it is so desperately conservative that if somebody hasn't built the machine you're already built before, you don't do anything new. So in fact, what's interesting in the technology of nuclear is we started out back in the 1950s with a plethora, a vast range of technologies. And over time, they commercially came down to essentially what is now on offer as a commercial large machine of pressurized water reactors like Coburg. And that was not because the other machines failed from a technological point of view, but because they failed from a management point of view. So, and it's interesting, the small modular reactors are largely going back to the technologies that were not fully commercialized in the 60s and seeing what their advantages are vis-a-vis the disadvantage of the large water-cooled reactors. But no, there's no obvious reason why no one's doing it. If someone gave me a blank check and I'd probably go back and try and do the same again. But that's not going to happen. So you're quite safe on that one. There is talk that there is a discussion ongoing of a small modular reactor being built with an overseas partner in South Africa, and certainly one of the options will be the Chinese high temperature gas core reactor, which is a pebble bed lookalike, except for a steam cycle. That answers the question.
Oh, yes, thank you very much for that. The next question is from Janet. Janet is asking, we occasionally hear of nuclear plants that will be able to use nuclear waste. Is this actually feasible, or will it be in the future?
The answer to that question is technically it's very doable. Of the nuclear fuel that leaves Coburg having been used up at Coburg, about 95% of what is in that fuel assembly when it comes out is still usable as fuel in some reactors. And if you go back to the 1960s, there was a view of a need to build what are called breeder reactors. Just the physics for you, I apologize for physics. If you dig out uranium out of the ground, 0.7% of it is what's called U-235, and that's the stuff that we can use in a Coburg type reactor. And 99.3% is 238, which actually you can't really use in a Coburg, and it's actually basically not useful. So what you then do is you enrich the uranium, so you go from 0.7%, you remove a lot of the 238, and you get to about 5% 235. That fuel goes into Coburg, and when it comes out at the end of its 4.5 years in the plant, it's got about essentially something like 93% of the 238 is still 238. Some is plutonium and some is the 235 left over. You can reprocess that and use in Coburg type reactors the plutonium and the 235 again. The French do that to some extent. You can also build a reactor which, because of different physics, converts the 238 into plutonium, which is burnable as fuel, faster than it burns up the plutonium. It's called a breeder for that reason. It makes more fuel than it makes. That is technically been demonstrated by the British, the French, the Russians, the Chinese, the Indians. It's been done. Physics is understood. The problem is that the price of uranium is too low to justify doing that. And what it leads to is a problem. One of the reasons people are somewhat wary of disposing of spent nuclear fuel is in a future era, 95% of what we're putting in the ground could actually be used to fuel new reactors if you build light water breeder reactors. So that's the answer to that question. It's pure economics. At the moment, it's just not worth it. The reprocessing costs are greater than the cost of getting new uranium out the ground. And there's no shortage of uranium. The world is every few years there's a shortage, the price goes up, more mines are opened up, the price comes down. But there are more closed uranium mines than open uranium mines. I hope that answers that question. But yes, you can do it. Very doable, just not a very commercial activity at the moment.
Okay, that's very interesting. And then the next question is from Blessing Siabangandogu. Blessing is asking, why is Hinkley Point C in the UK taking this long and costing this much? And why is this in counter to the graphs you showed of the timeline to build nuclear power stations, which showed time getting shorter and shorter?
Hinkley Point C, I mentioned earlier that there is a real difference between those countries that have got standardized production machines that are running out and those countries doing it in the first time. So the Hinkley Point C is the first reactor being built in UK for 40 years. They've issued a whole pile of regulations that they're requiring to, so they've actually redesigned the French reactor to build it locally. They created a completely new construction organization to build it. And they've also done something really, in my view, inappropriate, in that they, because of the way the economics in UK works, they have got a contract that allows them to sell power, or was when it was contracted, at £95 a megawatt hour. And if you backfill that to the cost of the plant, or you look at the capital cost out in reverse and say, what is my capital cost to make that make sense? It was actually a very big number. So everybody is getting their pound of flesh. It's a bit like Medupi on steroids. In other words, everyone's doing it for the first time, everyone's learning, and everyone thinks there's an unlimited pot of money. It is probably the least successful project, nuclear project, I've seen in my career. I would comment that people say, therefore, it will cost that for us to do it. And I will strongly comment, you can look at the Egyptians, the Turks, Belarus, Bangladesh, etc. And all of them are building importing machines from an established supplier, or Pakistan, and doing it to high quality standards and to very competitive costs. It's one of a kind. They're building it to unique British standards, and it's costing a fortune. If I can just expand a bit more on that, it's quite interesting. When we built Coburg, one of the problems you've got is that the national regulations tend to be different country to country. And when you redesign something different standards, you end up with more costs because you're building a first of a class. And it was notable, one way that Coburg was kept cost effective when we built it, completely safe, was we accepted, our regulator essentially accepted, and they've said this for new build, they accept that they will adopt the codes and standards of the country of origin. They won't try and invent new codes and standards. And also, I remember when Coburg was built, we have a pile of pressure tanks on Coburg, built to French codes, and the South African factory inspector agreed that if a tank was under the nuclear license, he would accept the codes and standards of origination. What they're doing in UK is they're re-engineering everything to the UK codes and standards. So they've changed all the building sides slightly because of fire regulations. Not that better or worse, it is different. And a really good example of this is the difference between the, I think it's Hungarian nuclear power station they're buying from the Russians and the Belarus nuclear power station they're buying. These are both in Europe. One's in Hungary, one's in Belarus. And the one in Hungary is costing 30% more than the one in Belarus. And when you ask people as to why that happened, it was because Belarus said they would accept, they would have their own QA and their own QC, but they would accept the fundamental standards of the Russian design. Whereas the Hungarians said, no, we must build it to European standards. European standards aren't better, they're just different. So the Russians had to factor in about a 30% price increase to go through the entire engineering design again, and do that. So I want to emphasize that Hinkley Point C is the poster child of how not to do a nuclear project. And if we do a nuclear project here, it will be a turnkey contract with somebody who hopefully has got a track record and is carrying the risk of overruns themselves. Thank you.
Thank you. Well, we'll be just going through the questions as they are coming along. The one question here that I have from Mazia, it says, in terms of the nuclear waste management, are we not going to run out of nuclear waste management spaces as time goes on, as we continue using nuclear power stations?
I will give you an answer to that question, which is very simple. If you know Falputs, which is our waste site up in Northern Cape, is approximately 100 square kilometers. And it is, if you know the Northern Cape, the nearest town is Springbok, which is 100 kilometers away. It is in the middle of nowhere. The Americans have got a similar disposal site called Barnwell for the eastern USA nuclear plants. About 70 nuclear reactors use this as their repository. It is 1 square kilometer and it is almost in an urban area. So we have got space. you know, there's no question. The space we have sitting at foul puts is enough to literally do 1,000 times what we're currently doing as a nuclear program. It is and one of the reasons foul put was chosen was because it was recognized there was no commercial value in it. In other words, there was no minerals underground. There's almost no rainfall. It's virtually in the desert. So no, we have space. Our waste facilities are adequate for anything we can conceivably imagine. And in fact, there has been discussion historically, should we get people to pay us large amounts of money to take their nuclear waste? Because the cost involved is burying it is very low, but the international cost of disposal is quite high. So there was a discussion of that. It's not currently being discussed, but it's an interesting discussion.
Oh, it's really interesting to consider that we could actually now also take on other people's nuclear waste and also be able to basically bury it. Yeah, it's very interesting.
We could. It's not politically acceptable, but commercially, countries like Taiwan, for example, are desperate to find somewhere, on a small island, just to find somewhere to put their spent fuel. It's currently stored in casks, I showed earlier, but they would probably pay very expensive rates to have their spent fuel stored here. But I don't think it's going to happen for political reasons.
No, understood. Now we're going to move on to another set of questions, or this is basically two questions in one. The first one says, the issue of skills capability within the country that is always raised as well as a challenge when it comes to NPP operation. Can you provide an insight on that? That's the first question. Now, the second question says, the issue of new site location outside Western Cape relative to the waste disposal in Northern Cape. How feasible is that to have a NPP outside Western Cape?
Okay, well, the first one about skills, I can almost do a reverse argument and say, when they built this 4-unit plant I mentioned in Bracco, which is in the UAE in the Persian Gulf, they had a problem. They contracted to build it. The Koreans built it very well and very promptly, but they realized they hadn't got the management infrastructure to run a nuclear plant. And when I was CNO and ESCOM, we were losing staff en masse to go and work for the UAE. So we provided 140 senior management people, not willingly, but they just left because the money was better, to go and work in the UAE. So first comment is we have a resource base. We had about 1,000 people working on the PBMR at one point. So if we want to build new plants, we're going to get that skill set together. And I will comment that when ESCOM built Coburg, they started out with no skill set. In other words, I think when Coburg was ordered by ESCOM, there were 13 people in the nuclear department of ESCOM at the time. So we're pretty well placed to skill. Coburg's run very effectively for the last 40 years. Staff have turned over, you train them. I don't see a problem with that at all. So I'm not in the least bit concerned at the skill set. If you build the project, the people will come. When I did PBMR project, when it started out, we had no idea how high temperature gas cooled reactors worked. I'm 93 now, and within 5 years, we were the world's experts in the field. So I don't think it's a big issue. What was the second question again, Salini?
Let me repeat it for you.
Waste movement. You can move waste. I mean, there is not much to nuclear waste. It's a lorry. You've got to drive a lorry somewhere. I mean, it's already 600 kilometers away from Coburg up to the foul puts. So no, there's no particular problem. You just drive the lorries there. Moving nuclear waste around is not a challenge. It's not really a safety issue. The only problem was certainly with spent fuel being moved around is not that you're going to release nuclear activity, but if you drive your car into a spent fuel cask, it is 100 tons of concrete, and your car will cease to exist. So there has not been a single nuclear waste transport accident causing any health issues anywhere in the world in the last 70 years. That's a pretty good record, I think. We can. It does better than liquefied petroleum gas, which explodes and kills people.
Yes, we've had many of those incidents, well, throughout recorded in the world, and yeah, you rarely hear about any nuclear transportation accidents having happened, or yeah. Well, in that case, we're gonna move on to our last question for the session. Hopefully, it's our last question. It's coming from Janet. It says, if it was up to you, what type of reactor would you choose? Large, water-cooled, or modular? And which country would you choose to supply the technology?
Okay, because you've asked a very, very pertinent question. In the supposed 2,500 megawatts of nuclear that's presently on the proposal, there is a proposal to do two things. One is to commit and turnkey contract for a large 1,000 megawatt class, 2 times 1,000 megawatts or so, nuclear plant like Coburg. In other words, Coburg 3 and 4 possibly, or Tatespunt in the Eastern Cape. And quite simply, at the moment, if you're buying one of those, my answer would be you go out to open tender. It's a very common, it's like buying a class of motor car. They're all very similar. It's a question of economics and who can do it better. So my answer is I'll be going out with an open tender. I would assume that the winner of that, not the assumption, of that tender would be either the South Koreans, the Russians, or the Chinese, because they're the guys who are currently doing it and doing it quite well. So that's my guess there. In terms of the other programming, I'll come back to which one I choose. There is a proposal, a way forward that says we'll build the first small modular reactor at Nexa in the next 10 years as the lead machine for the African deployment, and also deployment on the existing ESCOM coal fleet as they decommission. I think that machine, technically, I would want to have a high temperature machine because I think process heat is an important thing. And therefore you're looking possibly at a pebble bed reactor. I clearly bias towards that personally. And as to which will be the successful one, it depends on how those projects work out. Small modular reactors, I know the economics very well, promise under mass production very competitive costs. So large reactors in an idealized world are, the bigger you are, the more cost effective you are. That's pretty much a standard rule in industry. But you don't build enough large reactors to get into mass production, whereas in small reactors you get to mass production much quicker. So the question is, what's the cost differential? So my view would be this country should be going for both. One off on a small modular reactor, get the licensing, get the regulation, find out what really is involved in getting an operating one. And then we can have a basis of saying we know what the costs really are, not what we think they might be. And secondly, go for a large reactor and see if we can build a large reactor program. If you ask me an ideal world, if I was, given a magic wand, I would like to build large PWRs at Coburg, push Coburg up to 4,000 to 6,000 megawatts, put 4,000 megawatts at Tatespunt in the Eastern Cape, just next to PE, and I like to put another 4,000 megawatts on the Eastern Cape KZN border. And that would give us 600 kilometers apart, 3 loads, 3 power centers to support the development of the country. It would also feed Durban from the south. So, because Durban's currently only fed coming over the mountain from Gauteng, from Mpumalanga. I would then like to run a small modular reactor program to actually put small modular reactors both on the existing ESCOM coal fleet and possibly on large customers like Sasol, where you can start giving process heat directly into the plant. I believe that would be a good solution. I believe it would also avoid the need to put all this transmission system we're currently talking about in, because the nice thing about nuclear is there's a famous joke which said solar's all right, but nuclear works all night. And conceptually, we're saying is that you're building a massive transmission system because of the intermittency, and you don't know where the power's coming from. Whereas if you put nuclear plant in, you know you're putting it. Coburg has got a link to the grid, put 2,000 megawatts to the grid, occasionally 1,000 megawatts. But if it was 4 machines, that would be 4,000 to occasionally 3,000, and you've got stability. Whereas the renewable industry says, well, don't worry, we'll store the power somewhere, somehow at some cost. And I'm not sure that actually works out. Certainly, if you ask the Germans on that situation. Just a complete aside, but I'll chuck it in the discussion. What is very interesting for those who are following the power industry is the Norwegian problem with Germany. Germany, as you know, is very large into renewables and is basically sitting in the middle of Europe. And when it's got too much power because the wind is blowing and the sun is shining, it exports very cheap power to the neighboring states. And when it's got not enough power because it's winter and there's no wind blowing, it imports power from the neighboring states. And the Norwegians, who have got 2 big cables across the Baltic into Germany, are saying, we're going to cut the cables because you are so messing up our economics in Norway that we think they're a mistake. I think we're starting to see the beginning of the problems with intermittency and storage, which haven't been fully explored in the world to date. Okay, was that the last question, Salidi, or is there more? I will keep going until I'm told to stop.
This is the final question, and from here, just closing up. Well, it's also touching a little bit on what you had just mentioned now about putting in modular projects in different sites all across the country. Well, this question from Rodney simply says, where would new nuclear sites be in South Africa?
Well, I've said, to me at the moment, and again, I'm going to mention my personal views. I said already, we've got the site in the Western Cape, which is Eskom's nuclear sites are very large. Coburg's site is like 10 kilometers, 11 kilometers long. So there's space there for literally 10 gigawatts of power if we want to. Similarly, we've got the site in Pacepunt, which is near Jeffreys Bay. And that's another site I'd put it on. The other site, clearly, I would like to, this is a personal view, and I think we should put a site on the, on the Eastern Cape, KZN border, to feed into, to also develop that region, which needs all the development you can get. On the small modular reactors, the logical thing is to go into the Eskom existing coal stations, and as we decommission them, to build a comparable amount of plant on those sites to avoid grid expansion. So those are the obvious ones. The less obvious one, and I'll use is when you start talking about real decarbonization, you've got process heat applications to get rid of. Now, I'll give you an example. In this country today, we have Sasol, which I think I'm right in saying, one of your members may know better than I do, I think has about 8,000 megawatts thermal of boiler to provide steam to drive the chemical process. So one of the things why I'm quite keen, the SMR, the small modular reactor, has a high temperature option, be it lead cooled or sodium cooled or molten salt or high temperature gas cooled reactor. You would actually put those on the site and would let you directly feed hot. You would have the process heat would be fed straight into the commercial plant. So those are my sort of thoughts. But at the moment, Coburg, Pacepunt, Eskom, Pelindaba, where Nexa is for the first SMR, and then roll them out onto the Eskom coal fleet sites and avoid grid disturbance, and also avoid destroying communities. Because if you take something like Komati, when you shut the power station down, you shut down the mine, you shut down the village.
Yes.
But if you put a new power station there, you keep it alive. So the socioeconomic benefit of just simply putting Komati, Camden, Hendrina, just take those plants out, they're big sites, and put SMRs in their place. And you can keep Mpumalanga alive. Otherwise, Mpumalanga will become a very poor mealie farm.
Well, that was our final question for the webinar. Thank you very much, Professor David. It has been very insightful, very informative, and for all the people who are basically new to the topic of, nuclear energy like myself. I've learned a lot, and hopefully the same sentiment goes to the viewers and also to the experts who delivered questions. Thank you very much for the participation. And yeah, it was definitely a great interaction, and thank you a lot.
Thank you very much, Toledi and David. Thank you so much for joining us. Ladies and gentlemen, I just want to bring to your attention in the chat box, you'll see if you want to register for the SAIEE Nuclear Chapter webinar on the 19th of February at 11:15 a.m. We'll be unpacking the operating experience with respect to the Koeberg long-term operations presented by Ms. Bravans Mashele, who's a technical plant manager at Koeberg. So I'll give you a few minutes to click on that link and register. It is free to attend. And thank you very much for joining us this afternoon. And Toledi, thank you for hosting us, and to the Central Gauteng Centre for bringing this expert to our fields here, Prof. David Nichols. Thank you very much, everyone, and have a lovely evening until we meet next time. Goodbye.
Bye.
Bye.